Yeah, so in slightly more detail, the plan for today is I'm going to spend a lot of time sort of recontextualizing things that we talked about the um, in the presentation last week by Siphon, uh, and then the goal is going to be to say something about three classification problems, which are similar to one of these big headline results that Siphon mentioned from before, the classification of groups, finite subgroups of the orthogonal group. And then, if there's any time, I'd like to say a few things about the sort of general story that Artin has been building. I think that Artin had made a somewhat strange decision, which now, looking back on it, I understand a lot better. But the first time I was looking through this book, I certainly was a little bit confused as to why the group actions are introduced in the way that they are. And that's something that you can't get from the book, or at least it's very difficult to get from the book as a new reader. And so perhaps that's something where I can be of slightly more more value than the text. Um, but yeah, so let me remind you of a couple of quick things, starting with the technology that we developed. Um, so um, last week. Okay, so the big central object here is the group of motions. Uh, Group of rigid motions. So these are distance preserving maps and I think that we talked about it in the plane, but I'm going to sort of generalize as much as I can to higher dimensional spaces. Not everything I say today will be generalizable in that way, but we'll try to keep things at the appropriate level. Um, and then there's another group that sits inside of MD, which was not, I guess, technically introduced last week, but is maybe a more familiar object, which is I'm going to call sort of script O um, for the subgroup. Hello, fixing the origin. Right, so it's called scriptio because it's the orthogonal group. And at any time when the dimension isn't going to matter, which will be occasionally, I'll just omit these subscripts. Like, I could write OD, MD, or I can just write O is less than M with the dimension sort of somewhere in the air. This is not the only distinguished subgroup of M that we thought about. So there's this subgroup T, which is the subgroup of translations. These do not fix the origin. They don't fix any point. Right? So in other words, x goes to x plus a. Uh, will denote this transformation by t sub a. Um, and this is this isomorphic in a sort of very natural way to this, just picking out that number a, or I guess in general this vector a. Um, uh, so occasionally, Artin likes to write, think about subgroups of RD, and what he's talking about is the additive group, that vector space with respect to addition, which is going to be isomorphic to the translations. And he's a little bit fluid about the way that he talks about one versus the other. Um, okay, and I think there was one more thing, yeah, which is there was this map, this map that produced this object called the point group. So Artin calls it phi. It's a map from M to O. And it's a map that takes uh, a, a rigid motion, which perhaps we write as a translation, or excuse me, some orthogonal thing transformation followed by a translation. Um, and it just forgets about the translation. So that does, that is a rigid motion there at the front of that arrow. Uh, it is still a rigid motion at the back of the arrow, but it now fixes the origin because nothing in the orthogonal group moves that origin point. Yeah, alpha is an arbitrary element in O. So perhaps as a better way of answering this question, Kirby, let me remind you of something that's a little bit older than last week. Um, but remind you of proposition. Uh, okay, so I'm going to write 4.5.20. So here I'm in chapter 4. Uh, like that. And what this proposition says, although it said it in slightly different language, is that M as a group is equal to the product T times O. So what does this mean? So this was, if you want to go check this out, this was from Red's lecture 2 weeks ago. Um, we're talking about section 4.5. The way that it's described in the book is that the words any rigid motion is a proposition. Well, maybe it can be written um, in the form x sends plus b. Being very suggestive about things here. I guess I'll write this for some alpha in the orthogonal group, and some v in translation. And I guess if I'm going to be maybe really careful about it, I should write v is actually a vector, right? But that's sort of the same thing. So this alpha in red is the same as this alpha over here. It just means that um, right. So if you think about what this red map is doing, um, well, the first thing that it does is it takes the vector x and it applies this map alpha to it, this orthogonal transformation, and then it adds v to that, right? Which is precisely what it would do if it was, if it was this map, right? First, alpha x would be first apply alpha to x and then add v. Does that answer the question, Kirby? Excellent. Um, right. So it's not entirely obvious that this thing right here is yeah. This is not just like a function. This is in fact a group homomorphism, and that shouldn't be immediately obvious to you. Um, Homomorphism. Um, but it happens to be true um, because we can do a little bit of work here. Um, if we say, well, on yeah, we say on the left hand side, we have uh, T alpha, right? So maybe one element of the rigid motions, and then we do a different translation and a different orthogonal action. Um, so how does this act on some vector x? Well, it's going to do goodness knows what to x, right, with from this beta. Um, but beta x. plus, or maybe sorry, the right way to write this is maybe TV alpha times, or excuse me, applied to the vector beta x, because this is again sort of by this red characterization that we have. And then we do it again, right? So this is so alpha beta, or beta x plus w. Keep that where it's supposed to be. Oh goodness, what's going on? Does the audio fixed? Yeah, it looks like the audio is fixed. And sorry, and I'm not done. Plus b. So yeah, again, right? That's how TV alpha works. It takes the vector that you plug into it, and it multiplies it by alpha, and then adds v. And we finish this off with beta x plus alpha w plus v. Okay, and so what is this? Well, notice that this thing right here is just some vector. So this whole thing is going to be, uh, we could rewrite this as a translation where we translate by that vector. Uh, After uh, doing the transformation alpha beta, the orthogonal transformation. And so now if we forget about, if we apply this phi map and we forget about things, then this would just become alpha beta. And this would become, again, you forget about the translation, so it would just be alpha beta. X, and these are indeed the same. So certainly something like this is not always true. If you just happen to have some group um, that is the product of two of its subgroups, and it's not like the direct product, right? It's not one of these crosses that we talked about or these direct sums we talked about earlier. If it's just some any element can be written as the product of one element in subgroup A, one element in subgroup B. It's certainly not true that if you just forget about one of the subgroups, that the resulting map will be a homomorphism. However, it's true in this case, and based on things we've generally talked about sometimes subgroups are special, you might imagine that there's a normality condition going on, and that's indeed the case, but we're going to sort of leave that aside. Um, so I think that is the majority of the technology that we developed there. We've got our three main subgroups, the group of rigid motions, the orthogonal group, and the group of translations, as well as a couple of relationships between them, right? M is equal to T times O, as well as this group homomorphism that maps from M to O. All right, so that's the technology, and we're going to, in the last lectures, I think, use this to prove a couple of theorems, and I want to remind you about what I think are going to be the headline results, certainly the ones that are most relevant for the discussion today. Um, so theorems. Uh, so one was this classification. We had two classification subgroups last time, and yeah, let's. So one of them is in the text as theorem 3.1. Okay, and now everything else is going to be from chapter 5, I think. I'm going to omit the chapter. Um, but this first classification theorem was a subgroup. Sorry, was asking about finite subgroups of the orthogonal. Not general orthogonal groups, specifically the orthogonal transformations of the plane. Um, so if we have a group here, a subgroup there, which is finite, then there exists, no, sorry, then it must be either, um, well, it must be either cyclic or dihedral, but we can say maybe even more than that. We can say exactly what this thing is generated by. If it's cyclic, it has to be generated by a rotation of angle, some integer divisor of 2 pi. And if it's dihedral, then it has to be generated by that element as well as the so-called standard reflection. Um, Actually, no, that's not true. So there is this notion of the standard reflection, which is the reflection. Artin defines that as the reflection through the x-axis. But in general, the group could sort of be tilted, right? Dihedral, but tilted a little bit. So that's one of them. Uh, Talk about another classification result while we're here. Um, and this one I didn't see where exactly it is in the text. I think it is there. I kind of remember seeing it, but I wasn't able to locate it. So if anybody wants to point out that reference to me, I would be appreciative of that. But it's this one about discrete subgroups of R1. Maybe I'll give myself a little space in case somebody does have that. Discrete. And maybe I'll use different letters for each of these groups since they're going to sort of have a very different character. So of R, or we could think about that as being the one-dimensional translation group. And it must be okay. For some, you important thing to note is that if A is 0, and when A is 0, that leads to just H being the simple group, or excuse me, the yes, simple group, but although actually I think this group is not simple. The trivial group. And then just one more for fun. Um, Actually, because it's going to give us a very sort of cheap win at the beginning of the new material, is this theorem 3.0. Oh gosh, I'm sorry, I made a mistake here. The theorem that I said from before is theorem 3.4. Um, it is the I'll look for the notes again. um, oh boy. Well, folks, we'll get there. It's the other theorem I wanted to write down, which is 3.1. So just correct that real quick. So this one up here at the top is 3.4. Um, Number 3 is 3.1. Which says that if ooh, I need another GHJ. Um, so if we have a subgroup of motions and it's finite. So here, notice the difference between these two conditions. This one says that it's finite and is contained in the orthogonal group and also restricted to dimension 2. This one, even if we restricted it to dimension 2, it's still a little bit different because it's a subgroup of the group of motions, so we don't necessarily have to fix the origin. But even though we don't have to fix the origin, the remarkable thing about this theorem is that it says that if it's finite, then it fixes something. So fixed point. And what I mean by this is, I mean this in sort of the strongest sense possible. Um, um, in the space, just that. Uh, if I act on it by a group element, I get the element back itself. But not just this, but it's true for any group element. So there's a single point which is fixed by every group element. It's a much easier theorem that for non-translations that there is some point that is fixed by any element, but that's a much weaker result, right? Because that would allow the point to change around based on the element. But here we're saying there's a single point that works for every element. So far, I hope that I haven't said too much that's unfamiliar. Most of these words were at least mentioned by Xiphon from before. So I'm not going to make any attempt to prove any of these things in particular, um, beyond the morphism proof that we did a bit earlier. But are there questions sort of about the statements that we have here before we start getting into the meat for today? I will back up a little bit so that we can see more. So if somebody is still typing, feel free to keep doing that, um, and I will respond to you when I get it. But otherwise, let's keep going. Checking my time here. Okay. So I want to. So I said that after we did some review stuff, we'd be talking about a couple of classification results. And when I say classification results, just to sort of drive this point home, I'm thinking about things like these. These are right, and they're classifications in the sense that at the beginning, the only thing that I told you is that the group has to be finite. It has to be a finite subgroup of something, right? But at the end, or it has to be a discrete subgroup of something. But at the end, I give you a very, very strong statement about what all of the possibilities are. Tells you what every uh, every subgroup, but perhaps with some adjective on. And so Arden is sort of in this part of chapter 5 is really in the business of proving these classification theorems. And so like I said, there are a few more. So other things we might want, perhaps, um, can sort of brainstorm here. Um, so what else do we want? Um, well, I told you sort of at the beginning that this was the finite groups. Let me try that again. The finite subgroups of the orthogonal group. And then I sort of made a point about this, like, okay, but that's maybe different from the finite groups of the rigid motions. So perhaps you could ask for that, right? Um, maybe uh, 1 plus 3, uh, classify all finite subgroups of M2, I guess. You could say, hey, why stick in 2 dimensions? Can you tell me anything about uh, classify all finite subgroups of perhaps higher orthogonal groups? And then we could say like, oh, what about discrete groups? So perhaps extend 2 to higher dimension. Uh, okay, we'd have to remind ourselves, sort of think carefully about what discrete means in that context, but um, fine. And then perhaps maybe discrete subgroups of M2. So maybe I didn't need to write the words classify all 4 different times, but so we can sort of do well, we can actually do all of these, but we will not today actually do all of these. I will not even sort of state most of these results. But what we can do is a couple of things. So I will sort of tell you what Artin does with these things. So um, here, um, this is maybe the one. I don't know, maybe that's the hardest one to explain, so we'll come back to it. So this one turns out to be easy. We'll do it right away. Um, this one turns out to be hard, and takes up sort of the back half of section. Uh, excuse me, 5.4. This one is almost in 5.9. Although he skims out a little bit. He says, I won't tell you all the subgroups of the orthogonal group. I'm only going to tell you the subgroups of the special orthogonal group, right? The things that have determinant 1 as matrices instead of determinant plus and minus 1. Okay, so it's a little bit of a cop out, but you could maybe imagine how to sort of extend those ideas. Um, and this one is I should say for d equals 3. Um, yeah, that's important. um, and this is done exactly in for d equals 2 in proposition 4.5. And the proof is highly suggestive about how you would do it in higher dimension. So when I say that these things are sort of like almost done, um, Uh, I guess so. The almost there refers to the special orthogonal group, but Artin never sort of goes the full way, and he does this for a couple of reasons. One is that just that there are a lot of computations, and also a lot of those computations are very similar to each other. So what Artin chooses to do instead is to sort of go through a single subcase of in particular, I'm thinking about this last result. Uh, so he writes down a single subcase and sort of goes through all the complications, and then says sort of like the other cases are similar, and they are right, even if that's maybe not the most satisfying thing. Some of those details he then leaves as exercises, and I guess technically one of the exercises is sort of prove that the things that we've written down so far are the only things possible. So I guess technically in the exercises it sort of ends that way, but some of the cases are sort of structured, right? You sort of walks you through it in a sort of stepping you down, right? First, he gave you this one subcase that he does in complete detail in the text, and then he says, okay, now here's what you should do for if you want to deal with this other subcase in the exercises, and then finally, okay, and then deal with the other ones yourself. So let's move into this finite subgroup of M2 thing. Um, and I'm going to do it right here, actually, because it's going to use these two. Well, it's going to use 1 and 3 sort of very, very close, closely. Okay, so the theorem, new theorem, um, so 1 plus 3, um, which is that if, and maybe I'll have to give up on my we could keep going. If K is a subgroup of M2, and it's still finite, right? That's the condition we're playing with here. Um, then it still must be either Cn or Dn, and we can even say exactly what uh, generates those things. And I'm going to write it in perhaps a somewhat annoying way, but uh, not altogether outlandish, which is that it's going to be t of times rho 2 pi over n times t of minus e. Okay, so that's a single group element. Ah, sorry. Uh, yeah, let me see what I can do about that. Yeah, thank you, Anders, for the for the reminder. Hopefully it should be gone. Excellent. Good to hear. Right, so to finish this thought, this is a single group element, right? And it's sort of a rotation, but we've conjugated it by these translation elements. And similarly, we're going to do exactly the same thing for the dihedral group. It's TV rho 2 pi over n, t of minus v, and we need to do the reflection as well, and that's going to be TV rho 2 pi over n. Excuse me, sorry. What am I talking about? We need this to be a reflection. Um, Now, of course, we could simplify this, right? I told you from before everything could be written as first an orthogonal group element and then a um, first an orthogonal group element and then a translation. And so here I've written it in a slightly different form, and we could sort of go through the effort to figure out what that is, but somehow that's not the point that I want to emphasize here. Um, if there's any subtlety to this result, I think we have had some sound disturbance. Not from you, Kirby, but from outside. Uh, You're good. You're good. Um, yeah, if there's any subtlety at all to this result, it's that this v that shows up here is the same v every time, right? And maybe that the only place where that really is interesting is down here for the dihedral group. Um, you can conjugate a uh, by the same group element, or excuse me, by the same vector, right? Same translation, for both the reflection and the rotations, and that's all can work out. Okay, quick proof. So by theorem 3.1, just check some things real quick. Okay, by theorem 3.1, we know that uh, k has some fixed point. And this fixed point is going to be precisely the vector v that's going to show up in this from up above. Uh, so to emphasize that I'm not using the notation from before, but I'm just going to call it uh, v, and it's going to happen to be the same as the notation from before. No problem, Mohammed. Thank you so much for joining us. So we'll call this fixed point v. I don't know anything about it, but I know it exists. Um, and then um, so consider um, the uh, the group subgroup uh, TV times K TV inverse, right? And sorry, of course, that's not a subgroup of K, but that's a subgroup of M2. Well, if you take an arbitrary element in K, um, okay, then how is that sort of this new element going to act on X? Excuse me, actually, I'm going to ask how it acts on V. Sorry, I'm going to need just a second here. I don't want to consider this subgroup. Sorry, I want to consider this subgroup. So I only multiply by v inverse. I only do the translation at the beginning. And we'll get there. We'll get to the left translation as well. But for right now, it's easy to compute what happens here. Um, Goodness gracious, hold on. Let me. I understand what's going on here now. I'm going to make one more attempt to prove this. I claimed it was easy, so I should hopefully be able to convince you of that as well. But if not, well, then instead of seeing me sort of flounder around here, we'll try to get to a point. Um, okay, so I believe that I want to call this thing. I want to call this thing minus v actually. Um, so I'm going back to the subgroup that I had before, and I don't want to think about what it does to v. I want to think about what it does to 0. This is why I was confused. Um, okay, so starting things out, by definition, this is tvg of minus v, because we've translated 0 by minus v, so there it is. And now by this theorem from before, um, minus v is a fixed point. And so that means that g of minus v is just minus v. So this equality follows by the fact that minus v is a fixed point. And then, uh, again, by definition, I translate by v, and this becomes 0. Okay, I claim that we're done, and I would not blame you if you don't believe me. Okay, so what have we done here? What we've just done is we've shown that in this new subgroup, um, in this blue subgroup, um, we now fix every every single element in this new subgroup fixes the origin. Right? And so while I said that this group was a subgroup of M2, it's in fact a subgroup of the orthogonal group. In fact, this group here is not just a subgroup of the group of motions, but is a subgroup of the orthogonal group. And now we get to apply theorem 3.4. Which hopefully is still on screen. 3.4 says that we know every finite subgroup of the orthogonal group, or at least in dimension 2. And so we know exactly what this group looks like. We know what this blue subgroup looks like. But we also know exactly how that blue subgroup is related to our original group, right? It's just a translation on one side and then a translation on the other side. Um, and therefore, we get these specific pictures. This specific picture for these generators as well. Okay. I think what I'd like to do is that since we're at about 50 minutes, I'm going to uh, call pause right here. So we'll come back and continue talking about some of these other classification theorems. In the future, we won't go through their proofs in quite so quite so carefully. We'll definitely be a little more sketchy. But if you have further questions about what's going on here, or if you just need some time to process it, I'll leave it up on screen. Um, in any case, let's say 5 minutes. So we'll come back at 27 past the hour. I encourage you to stand up, stretch, get something to drink if you don't already have it, and we'll see you back real soon. We welcome you back. Okay. So we were in the middle of thinking about these classification theorems. Um, and one of them I sort of said was not so bad. Um, and um, and I don't know. You can tell me whether you thought my proof convinced you that it wasn't so bad, but um, there is another thing we should be there's another one that's sort of in this category of at least I don't want to prove it. It's sort of still sort of pretty involved to prove it, but I at least don't mind stating it in its entirety, which is this classification of subgroups of L, excuse me, subgroups L of the word is completely failing me. Um, of the group of translations, or the additive group R2. So let's put this down, and again, this is proposition 1.5, and I'll only write down the two-dimensional version just to save us some translation headache when we start to use this thing, perhaps. Um, so every discrete, right, subgroup contained in R squared plus uh, oh, that's not the correct order of those symbols, or equivalently, D2 is either 0. I don't know if that came through to all of you, but or it is maybe to emphasize the similarity to the. I think I'll still at least put it in the correct order. ZV. So this is N V for N is in Z. Uh, and for some V is in R squared. Or third possibility, uh, it could be NB plus MW for N and M are arbitrary integers, uh, and for fixed vectors V and W and R squared. Again, this is I'm not going to prove this. It's remarkably tricky, um, and the reason sort of why it becomes difficult is because of this condition here, this discreteness condition. Like this is not really a very group theoretic condition. It's really a topological condition or a geometric condition. Um, but just as a reminder, Artin defines this in a specific way. Um, so Artin's definition of this is that there exists uh, an a real number epsilon, which is bigger than zero, strictly bigger than zero. So that um, so there he puts two conditions here. If t v is in L, let me be generic here. So if TV is in the group, um, then the length of V is less than epsilon. I think less than or equal to for Artin. And if you have a rotation, this is a rotation fixing the origin, but through some angle theta, then theta theta could be negative, but um, aside from the sign, it has to be smaller than epsilon. In other words, there are no arbitrarily small uh, movements, either translational movements or rotational movements. Now, this is the only part of the this theorem that doesn't sort of generalize very quickly to higher dimension is you have to create the correct notion of what a discrete subgroup in higher dimension is. In general, this is using this Artin's plan of like, oh, just make sure that your parameters are small is perhaps doable, but maybe not the most fun thing. Um, but you can sort of get away with this for this theorem because it's a discrete condition for a for the additive subgroup, and so in fact there are no rotational elements in this additive group, um, and so you only have to worry about what it means for to have small, or excuse me, to not have small translations, which this these words generalize literally to that context. And so sorry, I think I hope this was clear from context, but just to be very explicit, uh, subgroup of M2 is discrete if this condition is satisfied. For those of you who have seen this kind of material before, who are sort of coming back to enrich yourself and are not learning this for the first time, I think it's a worthwhile exercise to think about what the proper generalization of this theorem is for higher dimension, and see if you can use Artin's proof as sort of a base case to think about even just dimension three is um, a really worthwhile exercise if you want to really sort of believe you understand why this is true. We will do something else today. So to round out section 4.5, Artin then goes on to classify the so-called wallpaper groups. So Artin's final in section 4.5, or excuse me, 5.4. I think I said 4.5 that entire time, but I meant 5.4. Uh, is show maybe to classify the discrete in the sense mentioned before. Um, Classify discrete subgroups of group of motions. So we did finite, but can we generalize that to discrete? So these sort of mildly infinite subgroups. I will say that I mean, and I said this earlier, but maybe I'll write down that this mission is not entirely accomplished. um, Leaving a fair amount to the exercises, and we will follow in this tradition. We will not classify everything. But there are some steps that he takes that I want to retread here because I think they sort of lend to this wider point. Remember, there's sort of teased at the beginning of the lecture that there was maybe this bigger point that Artin was trying to make, um, and there's this lemma that he writes down at some point that I think is useful for telling that story, and that is the crystallo- crystallographic condition. Um, a will prove proof. Sure, we'll attempt to prove the crystallographic condition, I think he calls it restriction, which shows up for him as 4.11. So, I guess. Okay, theorem 4.11. And I did not copy it to my notes, which was very silly. So let me go make sure that I write it down correctly. Um, I think I'm going to rephrase this very, very slightly. Um, let H be a subgroup of uh, O2. Sorry, give me just one moment. I'm having some technical difficulties with the tablet actually, which is not where I expected the problems to arise. Uh, I'm gonna give this maybe a couple of minutes, and we'll see what we can do. So I suspect that if I just reset the drawing program, things will work out. Let's give it a shot. Uh, well, hopefully we are not curvy. There's a couple more things I was hoping to say. We were just having some technology troubles. It looks like that might have resolved things. Okay. So now go back here and start recording this screen. Bang. Bang. And perhaps we're back. We're back, except that. Okay, so I believe everybody should be seeing the correct the correct picture. Um, and this gave me plenty of time to perhaps think about uh, how I want to rephrase this precisely. But theorem 4.5, I think we were talking about that a little bit earlier. Did you have a question about this discrete subgroup? Oh, sorry, no, it's at the, I see. No, I'm just misreading what you're trying to tell me. Yes, I think you're seeing what we're supposed to be seeing. So, uh, let G be a discrete subgroup. That's the spirit. Thank you so much, everyone, for your patience. Um, 2, uh, whose um, subgroup of translations, which I'll call, I think, L, is non-trivial. Um, okay, so this is true, but I want to make things slightly easier on myself, and say that it's not. So it could be one of these three things. So non-trivial would be not 0, but I actually want it to be in this case. It turns out that somehow there's nothing really interesting in that male case, but let's just keep things simple. Whose group of translations is like two-dimensional. I think maybe a more proper phrase here would be rank 2. So precisely what I mean is from case above. Ah, then uh, H, which I'm defining as phi of G, um, is uh, yeah, and so remember what is phi? Phi is this homomorphism that sends a group of motions um, into the sends the group of motions into the orthogonal group. So I'm saying like, okay, I've got a bunch of I've got a bunch of motions. Let's apply phi to each of them and see what we get. So this is going to be a subgroup of the orthogonal group. And so it has either so it's either a cyclic or a dihedral, as we talked about from before. But that's not the conclusion of this theorem. Well, let me say either Cn or Dn. This is not news. So far, everything we've said is just covered by the classification of finite groups here. But the extra crystallographic restriction is that we know things about n. N is either 1, or 2, or 3, or 4, or 6. Okay. So if the numbers 1, 2, 3, 4, and 6 are familiar to you, it's probably because there's some sort of notion of um, like tiling the plane, right? Tessellations of the plane, which might be familiar to you. And so you might know that the only polygons, regular polygons that tessellate the plane, are rectangles, triangles, squares, uh, squares. Yeah, I say rectangles. In what sense is a rectangle? Sort of corresponds to the n equals 2 case here, or regular hexagons, or I guess line segments, right? Although that case is usually so degenerate that we ignore it. And in fact, these are, there's a very close relationship here. It's not an accident that these numbers are showing up. Um, do unigons and digons tile the plane? They do not, but we can sort of we can think about a digon as being being like this rectangle. It's sort of close enough for purpose. So these were discussed. These are creatures that were discussed in a well, in Xiphon's lecture, I believe. Right, and so they're sort of theoretical or ideal polygons. A unigon is something that has exactly one vertex and one edge. Um, and a digon has exactly two vertices and two edges. Um, like this. Um, and these, so the reason why you might bring up these things is because they are, uh, we somehow believe that dihedral groups are the symmetries of a particular shape in the plane, a regular polygon of some kind, right? And so this is a problem because it only works for n is bigger than 3, or at least you could pretend that it's a problem because it only works for n is bigger than 3. Um, but it turns out that you can sort of make this hack, right? You can create these ideal polygons, or which is ideal here meaning not actually a polygon, but um, that have the correct symmetry group, even though they don't technically satisfy the definition of a polygon. Of course, if you're not restricting yourself to regular polygons, then you don't have to get so exotic, right? If you just want something with dihedral symmetry, then a rectangle works perfectly well. Sorry, a D2 symmetry, right? Since you have both of those lines of reflection, but not a fourfold rotation like you would with a square. Yeah, thanks for the questions. I'm stumbling a little bit on this n equals one thing, but I think instead of sort of wandering around there, um, I'm just going to get on to this argument. Okay, so uh, maybe I'll finish this off by saying, phi. Just a reminder that phi is the map that sends. Uh, okay. So there's a couple of things to this proof, and now I'm looking at the clock. I think we can still. I think we can still do this. Um, the main thing that I want to argue here is not even for this proposition, which is or should be this theorem, which is quite remarkable. Although I guess he calls it a proposition, so maybe I should too. Um, but is this key lemma that shows up, um, and kind of does the big work in here. Um, so he calls this a proposition, but I think of this as like a lemma. So we're going to use this along the way. Point 10. And so same setup. We have a discrete subgroup of M. We have the group of translations. We have the point group H. Um, um, and I guess Artin calls this G bar. But if you remember from last lecture, I really dislike this bar notation, so I'm going to avoid it in most cases. Um, so G. Then here's the interesting statement. Um, the elements of H H. And so Artin's phrasing is carry LG to itself. In other words, so for every for every um, G in H, I guess I could call it H. Why not? For every H in H, um, and vector in G. So again, this is where he plays a little bit loose. The vector is really an element of R2, maybe not group there. It doesn't, and let me get to that. So for every, pretend that's the beginning of a sentence. So for every element of the group and every element of the lattice, then if you act, if you, yes, H is a motion. So you say what happens to V. Uh, then this, a priori, all you know is that this is some vector in R2. But in fact, what is true is that it is a vector in LG. So the interesting thing here is that this is not just in. I see typing in chat, so I'm pausing here. I see. So the reason why this is different from identity, and I agree, Kirby, that that's exactly how I should think about the identity. Um, is that I don't know that h of v is v, right? It could be some other element in the lattice, and usually will be. Um, but it is still in the lattice as opposed to just being some random vector, right, in the plane. So let's prove this. Okay. So by definition of H, or perhaps by definition of phi, but let me just say H, um, there is some G and G, so that H is equal to phi G. Right. H is just the set of elements, which happens to be a group, but it's just the set of elements that is the image of G under this map phi. So if it's in the image, then it had to come from somewhere. I'm not claiming that G is unique. It's just out there. Right? Um, uh, check. And so Artin says that G of sorry, H of V is the conjugate of V by. So why is this true? Because if you take G and now Artin does this, and he's a little bit more tactful about this than I was, but he makes this sort of trick, swapping out the vector v for the translation by that vector v. Uh, ah, right. So how are we going to start to compute this? Well, what we do is we say we know that because G is an element of the big group, which is in particular a subgroup of the group of motions, then G has to be written as a translation times um, an orthogonal group element. Um, and because we have, uh, sorry, this translation should be by a vector, not an angle. Um, we have a name for this. A rotation, and if it's the only things that exist inside of the orthogonal group O2 are the reflections and the rotations. So if it's a rotation, it's that, or it's a reflection. Sorry, other way around. If it's a reflection, it's the first thing. If it's a rotation, it's the second thing. Okay, and then we do some computations here. This is so start to write out everything properly. We get now. I'm really hoping that Artin is doing it in the same order that I am. Yes, okay. um, Flip these for ease of writing later. Okay, so TB phi. So that's G. And what should G inverse be? Well, we should flip the order of these things. We rotate by not by phi, but by negative phi. Undoes the action of multiplying by phi. And then we translate. To undo the translation by b, we translate by minus b. And so we saw earlier that we can simplify some of this. Um, if we have, this sure looks a lot like two group elements being multiplied together. Um, and so if we steal our formula from last time, then that's going to look like, oh, okay, I could do this, but I kind of want to do it the other way, actually. Rho is rho theta. So you translate by, right, you translate by the rotated vector, and then you translate by the rotated vector, and then you rotate by that vector. That cancels, leaving you with just okay. So these things cancel, and so do these, because even though they're not next to each other, they're once you cancel out the rotations, then everything is a translation, and so translations are commutative. I'm aware that this computation is perhaps a little bit messy. I hope this gives some indication about why um, I didn't want to didn't want to work too hard to go through all of these proofs. Okay, so I was supposed to show, however, that at the end I get h of v. Why is this h of v? Well, why is this h of v? It sure looks like, right, h of v is a vector, and so in this case, h is equal to theta. In this case, h is equal to that. Right, because remember, to when you pass through by this point group map, you just get rid of the translation. So those h's describe what's left. Um, and so h of v. This is so by definition, this is th of v. And again, we do this little trick. Uh, we say, okay, well, remember, translating by a vector is the same uh, as considering the vector by itself. Yeah, so I think what I want to do here is I want to remind you that it's the same trick as before, but write that, why that happens. Okay, are we done? Yes, yes, we are done. And the reason is that I'm supposed to believe that this element is sort of clearly in the, the webs. Do I believe such a thing? Um, I did at one point, and now it's escaping me. Um, all right, I'm currently looking at the proof in Artin, and I'm realizing I probably should have copied this idea down into my notes because Artin's being a little bit vague about this. Hey. Image. Okay, so let me sort of call this one off and say, so we would be done if we knew this is in G. Since then, the computation shows that H of V, after all is said and done, that's what we got, would be in LG, or would be equal to something in LG. And is this a case where we simply need to compute I think I am going to call it off here, just because I don't remember the idea. Um, but perhaps if I remember this, I'll definitely make a note of it in the server. And in any case, I'll try to write up exactly the question that I have and post it in the problems forum. So so perhaps we can crowdsource this. Um, okay, so I'm gonna pretend we're done. Okay. So, proofs aside, what do we have here? We have this statement that um, we're trying to we're trying to prove this classification, and along the way we have this crystallographic restriction, and along the way to the crystallographic restriction we have this proposition. Exercise for the viewer. I appreciate it, Kirby. Um, and what this sort of this workhorse is saying is that um, we have a we have this point group, this 5G H in our notation here, and that subgroup not just, it doesn't just send it doesn't just send the plane to itself, although that's certainly a requirement. It also sends the um, this lattice, this LG, uh, to itself as well. Okay. Um, so I had plans to say a few words about what's going on in section 4.9 as well, but I don't think that's going to end us today in a very satisfying place. So I will defer that to perhaps properly where it belongs after discussing the rest of chapter 5. Um, and instead highlight this point here. So this is some high level observation. Uh, High level not meaning complicated, but high level meaning sort of high, right? Abstracting a lot of the details. Um, so high level observation is that uh, to prove our classification result, in other words, to understand something about the group, sort of concretely, uh, we found this object. We found this secondary object, G, which was preserved, um, which was, yeah, preserved. Um, by sorted by the group, uh, despite being smaller than all of r squared. I cannot, but I appreciate the question. The question is, can you please sketch all the homomorphisms if possible? I can. Yeah, this gets very involved. Um, this is also a classification theorem, right? Because the I guess homomorphisms. That's not true. It is a classification theorem, but of a different kind of object. Um, if the question were to classify the automorphisms, so the automorphisms are themselves a group. Um, And so, now you're just asking to classify a different group. And for homomorphisms, it's even more involved than this, right? Because there are non-bijective homomorphisms that you have to worry about as well. It's a good question, but unfortunately, it's too good of a question. Uh, the only homomorphism that we're sort of using in this whole thing is the this phi map, right? The fly map that takes a motion, simple motion, sorry, a rigid motion, and says like, okay, I can write that motion as a orthogonal bit and followed by a translation, and just kill the translation, right? Uh, so That's the only homomorphism that we're sort of using in this whole story. So the reason why I wanted to say a few things about 4.9 is that excuse me, section 5.9 is that this observation shows up there as well. The object is different. Instead of being a lattice, it's actually sort of points that exist on a sphere. Um, that are called the poles. If you wanted to do some reading, sort of sneak peek ahead there, um, a lot of that section is understandable. There's one piece of technology that really uses the rest of the chapter. Um, but this observation sort of shines through there as well. And it was things like this that eventually led people to this this idea that perhaps we should be thinking about sort of axiomatically in the same way that we axiomatize the notion of addition and multiplication into the concept of a group. Perhaps we should also abstract this concept of like, oh, what does it mean for these things to be preserved, right? Um, and the resulting object there was a so-called group action or a G set. Um, uh, this group action is the sort of explicitly the subject of section 5.5. Uh, but maybe I should say and subject of the rest of the chapter. Sorry, you're you're seeing that delay on the writing, but hopefully all of the symbols are going to come out. Um, and so that this is a very good place for us to leave it today.